We're going to talk more about arrangement of capacitor. What do you understand by capacitor? Capacitor is like a device used for storing electric charge, and there are two several ways you can arrange a capacitor. Number one is arrangement in parallel and arrangement in series. Like for example, you see some diagrammatic expression like this. This is what you call capacitor in series. You see something like this. This is what refers to as capacitor in parallel. As you can see them, this one is in a straight line, but this one is breaks up. Can you see? So this is what refers to as capacitor in parallel, and this is what refers to as capacitor in series. But there are some notes. Note one thing, like some points. And in capacitor in parallel, there's always same potential difference. Same potential difference. That is the what? Potential difference. Capacitor in parallel. Capacitor in parallel has same potential difference all through. That is, the same potential difference in this one is also the same potential difference in this one. It's also the same potential difference present in this one too. So they have same potential difference in the capacitor. That is measured, is usually measured in volts. And they also have different charges. They have different charges, usually measured in coulomb. And you can see sometimes you see the symbol as Q, small letter Q. So this is the symbol. So now, capacitor in parallel, I said they have the same potential difference. That is, in all the capacitor, they have the same potential difference all through, but different charges. So the total charge is equal to Q1, this Q1, this Q2, and this Q3. So plus Q2 plus Q3, that is the overall charges in this capacitor. Q total is equal to Q1 plus Q2 plus Q3. This Q total is greater than any individual charge of a capacitor. Like Q total is greater than any individual charges. Like Q1 is greater than Q1 or Q2 or Q3. And there is one thing I want you to note is that the equivalent capacitance, like equivalent capacitance, which is regarded as the total capacitor, that is the C total of a parallel plate capacitor, a parallel capacitor is greater than any individual capacitor. That is, C total is greater than C1 or C2 or C3. That is, you know, this one is one capacitor, this is also another capacitor. So C1, C2, C3. The total capacitor, that is C1 total capacitor, that is C1 plus C2 plus C3, is greater than any of these individual capacitor, C1 or C2 or C3. You understand that? So the equivalent capacitance, which is regarded as total capacitor of a parallel capacitor, is greater than any individual capacitor. So how to calculate the total capacitor in parallel? In parallel is equal to C1 plus C2 plus C3. You understand? As C1 plus C2 plus C3. If there is C4, you can write C4. If there is C5, you can write plus C5. You understand? On to the infinity. Understand? So this is what refers to as capacitor in parallel. So the total capacitor in parallel is equal to C1 plus C2 plus C3 onto the infinity. And this is one of the example. If you see a diagram like this, you know that they are talking about capacitor in parallel, and how to calculate the total capacitor in this parallel plate capacitor is to write C1 plus C2 plus C3. That's total capacitor in this diagram. So now for total capacitor in series, this is the total capacitor in series. How do you calculate the total capacitor in series? Is equal to 1 over C total is equal to 1 over C1 plus 1 over C2 plus 1 over C3 onto the infinity. You understand? So to calculate the capacitor in series, you must use this formula. That is 1 over C total is equal to 1 over C1 plus 1 over C2 plus 1 over C3 onto the infinity. So that is how to calculate the total capacitor in series. Now, there are some important notice too in series, in calculation, in arrangement of capacitor in series. Example now, I said in capacitor in parallel, I said they have the same potential difference and different charges. And I also said the equivalent capacitance, which is the total capacitor of the parallel plate capacitor, is greater than any of the individual capacitor. So in this total capacitance in a series, you should notice that they have the same charges. You can see that they are opposite to each other. They have the same charges, which is usually measured in coulomb, having a symbol of Q. This is a symbol Q. They have the same charges, and they have different potential difference, different PD, potential difference, measured in volts, different, measured in volts. And now the equivalent capacitor, which is the total capacitor, equivalent capacitance, regarded as total capacitor of a series arrangement is lesser than any individual capacitor. Notice that the capacitance in parallel and capacitance in series, they are opposites in action, like they are antagonistic in nature. Parallel and capacitor in parallel, they have the same potential difference measured in volts. They have different charges measured in coulomb, and the total charge of a parallel plate capacitor is greater than any individual charge. Also note that the equivalent capacitance, which is regarded as the total capacitor of a parallel plate capacitor, is greater than any individual capacitor. So for capacitor in series, they have the same charges, Q, represented as Q for the symbol, different potential difference measured in volts, and the equivalent capacitance of a series arrangement is lesser than the individual capacitor. So that is all for capacitor in parallel and capacitor in series. So we move to energy stored in a capacitor. W is equal to 1 over 2 QV, where our Q is equal to charge and our V is equal to potential difference. As we all know that C is equal to, which is the capacitor, is equal to Q over V. So when you find this, you cross multiply, you get your Q is equal to CV, right? And you substitute your value of Q in the equation, which is CV. So W is equal to 1 over 2, that's our QCV, CV times V, that is what, 1 over 2 CV squared. So this is other equation, this is other formula you can use for energy stored in a capacitor. 1, 2. Other ways you can do 1 over 2 QV, where for you to calculate your VC, make V the subject of the formula, that is V is equal to Q over C. So 1 over 2, what's our Q? Q times V. So whenever you see your V, you substitute it as V is equal to Q over C. So Q over C, which is 1 over 2 Q square over C. That's Q times Q, Q square over C. So this is the other formula. The energy stored in a capacitor is also W, or energy, is equal to 1 over QV. Whenever you see And we all know that C is equal to Q over V. You cross multiply Q is equal to CV, right? Then whenever you see your Q, represent it with CV. So that is where I get my CV square. And 1 over 2 QV, Q times what's our V? V is equal to Q over C. So Q times Q, that's Q square over C. So this is, let's say this, let's represent with equation 3. Represent this one with equation 2 and represent this one with equation 3. Thank you very much.